So without further ado, let's start with the first speaker of today, which is Harsha Honnappa. Harsha received his PhDs from the University of Southern California in 2014 on the supervision of Rahul Jain and Amy Ward. And he has been an assistant professor at Purdue University since 2015. He has a broad range of research interests, which resulted in impressive work on stochastic modeling, machine learning, and stochastic optimization in games. He has served in several editorial boards, in particular OR Letters and Operations Research Journal. And today he will be talking about the sample complexity of offline reinforcement learning. Please go ahead, Harsha.
Thank you, Fiona. Just one correction. I just want to point out that I'm currently an associate professor. So, thank you. So first, I want to thank the organizers for inviting me to this really interesting and nice workshop. I attended the first version, so I'm very glad to be talking now. So today I'm going to talk about the sample complexity of offline reinforcement learning. This is joint work with my graduate student Imon Banerjee and colleague Vinayak Rao. Both of them are in the Department of Statistics here at Purdue. And at the outset, I want to point out that I'm not going to be talking about a specific service system or even present a method to do reinforcement learning. But I think that there is a sort of framework of thinking that is highly relevant to service engineering and the way that we as a community tend to think about data-driven problems. And so one of my missions has been to somehow bridge the gap between applied probability and the machine learning world. And the way that I've tried to do this is by working with machine learners like Vinayak, for instance. So let me give you an overview of the talk. So at the outset, I'm going to sort of contrast online reinforcement learning, which is sort of the standard formulation, which I'm sure everyone here is well familiar with. And then I'll contrast it with the offline paradigm, which I think is most relevant to the way that we think about service engineering. And then within offline reinforcement learning, there's a couple of flavors, and I'm going to focus on the so-called model-based offline reinforcement learning. And in particular, within model-based offline reinforcement learning, I'm going to talk about system identification and statistical inference for system identification. And more precisely, I'm going to talk about sample complexity bounds. So how many samples do you need to be certain that any sort of probabilistic errors that you're making are small? And in establishing these sample complexity bounds, we use different concentration inequalities, and different concentration inequalities give you different qualities of results. And I'm going to talk about a result that comes from using an Azuma-Hefting type bound, which turns out to be sort of suboptimal. And then I'm going to sort of show how you can improve that by using a Chernoff-Bernstein type bound. And then the Chernoff-Bernstein type bound actually lets us obtain a very sharp result on the sample complexity and also show the minimaxity of a specific estimator, very natural estimator in the setting that I'm going to show you. And then I'll end with some concluding thoughts. So let's start with talking about online reinforcement learning. So the standard notion of reinforcement learning is you have an agent, and the agent wants to compute an optimal policy or a value function, but it can't do it because it doesn't know what the dynamics of the stochastic environment are. So the agent takes actions and interacts with the environment. The environment sort of gives a feedback or reinforcement signal, which the agent then uses to learn, typically the value function, or in a model-based setting, you might try to learn like a policy function. So online RL has sort of been the primary focus of the RL literature. And it's, this type of learning is online in the sense that you get feedback continuously, right? You take an action and then you immediately gain some feedback. But there are problems with this paradigm, in particular in sort of settings where, it's sort of a safety critical situation or you're sort of risk averse. So think about like, a healthcare setting where you have to decide, for instance, staffing or routing or something, and you don't know the the arrival rates or service rates. So you have to somehow learn what a good policy is. It's not clear to me that you want to let an RL agent sort of run wild, trying to learn what an optimal policy is. simply because underlying reinforcement learning is this exploration-exploitation trade-off, right? In order to learn well, the agent has to sort of explore an experiment to figure out what's a good region in the state space and the action space. And this can, along the way, sort of lead to really suboptimal bad outcomes. And if you're in a risk-averse situation, this is not something that you want to do. And I think this is generally the setting for many service systems. So luckily, within the reinforcement learning world, there is an alternative model that may be more appropriate. And this is called as offline reinforcement learning. So the idea in offline reinforcement learning is you have a sort of so-called fixed logging or behavior policy, and you following this logging policy, you take actions and you still have an unknown stochastic environment and you still receive state and reinforcement or reward signals. But then you don't learn directly from that, but you put all of that information, the action that was taken, the states that you're transitioning to, and the rewards that were received into a database. So you collect all of this information into a database, and then subsequently the agent will learn from this database using some machine learning or some statistical estimation procedure, and you try to learn either a system model or estimate an optimal policy or a value function or whatever you're after. So in this sense, offline reinforcement learning is genuinely data-driven, right? So you have a fixed data set that you're trying to use to learn from. And typically this learning is performed on a database of interactions that are collected using, as I said, this fixed policy. The logging policy is typically unknown. And in fact, this is going to be the situation in almost any service system that you can imagine. The agent does not receive any feedback, as I said, from the environment. So in that sense, it is not online. It is totally offline in its learning. And because you don't have this immediate feedback, offline reinforcement learning is actually significantly harder than online reinforcement learning. And it naturally leads to a whole bunch of interesting, hard statistical, inferential, methodological questions that are wide open and people are still investigating this. And one of the difficulties in doing this sort of data-driven reinforcement learning is that you have to learn from a single path, or what I'm going to call as the trace of interaction. So a trace of interactions will consist of M tuples, SI, AI, and RI. SI is the state at time I. AI is the action that was taken at time I. And RI is the reward signal that was received at time I. And typically M, the number of such tuples that you observe is going to be finite, and it's just some number of interactions that you've had with the stochastic environment. This is clearly useful, as I said, in situations where either doing online learning is uneconomical, or it is dangerous or impractical. And you can immediately sort of imagine what these example situations may be: medical decision-making, service operations, inventory management, autonomous driving. So within the RL and machine learning communities, I think autonomous driving has been one of the driving motivators for this type of research. So just to fix these ideas, let me sort of illustrate it with a specific example from service engineering. So let's think about a situation where I want to sort of improve staffing in a service system. So maybe this is like a hospital outpatient clinic or an emergency room or something like that. So I have a multi-server queue. Let me say that each of these servers are heterogeneous in nature. So the service rates are mu1, mu2, and so on. I'm going to assume that these service rates are unknown. I'm also going to assume that the arrival rate is unknown to me. And the goal is to decide the number of servers when these service rates and arrival rates are unknown to you, but you can collect data on that relate to this. And your goal is to sort of minimize staffing costs and waiting times in some appropriate cost function. And when you think about the situation, data will be collected typically under some a pre-existing policy, right? So the hospital in the example that I gave you possibly has some routing policy already that they're comfortable with. It may not be optimal, but they're comfortable with it because it sort of fits within their safety parameters. So using this collected data, maybe then you want to try and improve the policy, try to find a better staffing policy, for instance. And this is, very naturally a data-driven or offline reinforcement learning setting. So it's very natural in the service engineering settings that we are interested in as a community. So now, talking about offline reinforcement learning, just like in the case of standard or classical online reinforcement learning, there are two flavors. One flavor is what you would call as model-free methods. So in model-free methods, you're trying to learn either an optimal value function or a policy without actually directly learning the underlying stochastic dynamics. And so broadly speaking, these these model-free methods use either approximate dynamic programming or importance sampling methods to learn the value or Q function, and often it's just trying to adapt in some way the online reinforcement learning literature to this setting. Unfortunately, it's also been shown that if you just try to adapt, you can't just throw an existing online RL method to this problem. It will do poorly. But even with these adaptations, it's been seen in the literature through both empirical experimentation as well as theoretical analysis that model-free offline RL can actually perform quite poorly in practice. In particular, and as you can imagine, since you have a fixed data set and you're trying to learn from this one fixed data set, whatever optimal policy or value function that you've learned using this from this logging policy will may not necessarily reflect reality, in the sense that the agent will eventually encounter new experiences or new sort of scenarios that it has not seen in the past. So therefore, this problem of distribution shift is really critical, and it really causes truly poor performance of model-free offline RL. And how to mitigate this question has been an important one within this particular community. I should note that this is not the focus of my talk. My focus in this talk is on what's called as model-based reinforcement learning, which is an alternative, which does mitigate this distribution shift problem to some extent. So model-based reinforcement learning typically involves two successive steps. The first step is model identification. Here you explicitly estimate, using either machine learning or some statistical estimation procedure, the underlying stochastic dynamics. Like you try to identify that stochastic model, and then you use that stochastic model to compute either an optimal policy or a value function. And the way you compute the optimal policy or value function is by using dynamic programming. So either value iteration, policy iteration, or maybe some approximate dynamic programming, depending on the complexity of your problem. So you estimate the stochastic dynamics, and then you learn a policy or value function based on it. And I think that the way that we as a community would tend to think about these sort of data-driven problems is sort of closer to this model than the online setting, I would say. And in this talk, I'm going to be focusing myself on this model identification part of this flow, and in particular, the statistical estimation problem. And it should be noted that there is a growing literature. So this is not something novel, clearly, but there is a significantly growing literature on model-based methods for offline RL. Very recently, for instance, you have these two methods. One is called as Morel, the other one is called as MOPO, that have been proposed. This was in 2020, and there's been hundreds and hundreds of citations of these papers. All of these methods basically fit that sort of flow chart that I showed you. So you have model identification followed by policy computation. What I am interested in as a theoretician is in statistical inference. So just ask yourself the following question. I'm solving this data-driven problem. Typically, I have a fixed amount of data. How can I trust this model? How can I be sure that I've learned, in particular, the system dynamics or the stochastic model accurately enough? And so therefore, statistical inference is really important. In particular, understanding error bounds and saying that I have enough samples to be sure that my errors are not going to be large. Or maybe I'm interested in consistency, or equivalently center limit theorems. So these are all crucial in order to have some sort of confidence and in order to effectively deploy these methods and these learned models in practice. So this talk, I'm going to provide the first sample complexity results for model identification and offline reinforcement learning. So before I get into those results, I do want to fix some of the notation and the model and the setting that I'm talking about. So I'm going to broadly use the term Markov decision process, or MDP. And to that, I mean, I will have a paired process, Xi and AI. Xi is my state process. AI is my control process. I am going to assume for simplicity that I have finite control and state spaces. I'm also going to use the term action and control interchangeably. So if I say action at some point, I really mean the control sequence. I'm also going to assume that underlying everything there is this filtered probability space that will never come up again. Like, I'm just not going to mention it again, but it sort of underlies everything. The control model. So typically the way that you would talk about the control model is through a policy function, right? So you will have an explicit function that maps states to actions, or maybe states to a probability distribution on the actions or controls. Here, I'm just going to say that my control sequence or action sequence is just adapted to this filtration. And then I'm also going to have a system model where the states will transition according to this sort of Markov kernel here. Okay, so based on my current state in action, my next state is going to be whatever it is. I'm going to move to a new state. And because of the generality of the control model, this pair process is not going to be Markov in general. So we have an estimation problem for a controlled or Markov decision process where the state action pair is not going to be Markov in general. And the estimator that I'm going to think about is an estimator for this transition probability, right? So this is sort of the system dynamics, and this is the object that I want to estimate. And the sort of natural estimator in this setting is just this ratio estimator, where I count the number of times that I see that I'm in state S, I take action L, and then I transition to state T, divided by the number of times that I was in the state action pair SL. Okay, very natural. The probabilistic error bound that I want to compute is the probability that I make an epsilon error between this true transition kernel and the estimated transition kernel with respect to some norm, and our results will be established with respect to the soup norm. Now, I should note that this question appears to be fairly simple, but it is somewhat non-standard in the sense that both the numerator and the denominator in this estimator are random, right? So that causes some problems, and so it's a slightly subtle question. So, but one can compute some fairly intuitive results. So to illustrate this, let's say that I fix two integers, right? So an integer NL and an integer NH. And then let's say that I look at the event, that I make an epsilon error for a fixed action L. And the number of times that I visit the state action pair S and L is between NL and NH. Now this probability is exponentially bounded. It's exponentially decaying, and the decay rate is entirely controlled by NL and NH. In other words, what this means is that to ensure that you have some sort of small probabilistic error or some notion of consistency, what you really need to do is control the number of times that you visit each state action pair. If you control the number of times that you visit each state action pair, in other words, you visit sufficiently many times, then you can ensure a small probabilistic error. So this naturally leads to the following three questions, in my opinion, in trying to answer this sort of statistical inferential question. So the first question is, what is the sample complexity of this estimation problem, right? So using this non-parametric estimator, what is the sample complexity? What is the minimal or precise number of samples that I require in an order sense in order to ensure a small enough probabilistic error? Second question is, when is this non-parametric estimator minimax? In other words, the sample complexity bounds that I get, when are they sharp? And the third one, which is sort of underlying both of these questions, is how does the logging policy? So the logging policy is the thing that we don't really know, right? So think about, go back to that service system example that I mentioned. The hospital, and we're thinking about a hospital situation, the hospital has some fixed policy. Who knows what the policy is, right? I mean, they decided to do something and it works. But I don't know what the structure of that policy is. I mean, I can't say that that policy is Markov, for instance. So I want to understand, if I assume certain things about this policy, I sort of lose conditions that I impose on this logging policy, how does it influence the bounds? So in order to address these questions, I need to introduce some assumptions and conditions on the MDP model, which is what I'm going to do next. So let's start with the control of the action sequence. So just to recall, we have the data consists of traces of state action pairs. So you can take the control sequence out of that. The logging policy, as I mentioned, is unknown. So the condition that I'm going to impose on this control sequence is basically that the gamma mixing coefficient is summable or bounded in the following sense, that for each m, there exists some constant c where these gamma mixing coefficients will sum in this way. Now, the gamma mixing coefficient basically says, how quickly do I forget that initial history, right? The initial history from time 0 to time I, how quickly do I forget it? How quickly does this control sequence forget it? Coming to the state sequence, here I'm going to impose a sort of weak mixing condition. Namely, I'm going to impose, again, sort of a summability condition that for every m, there exists some constant c theta where this weak mixing coefficient is bounded or less than or equal to c theta. Note that the weak mixing coefficient is really the weak ergodicity coefficient or Dobrushin's coefficient in the case where if you were only looking at an inhomogeneous Markov chain, right? So it's sort of quantifying merging of a inhomogeneous Markov chain. Note the following. It's not that assumption 1 can imply assumption 2. In general, you will require both assumptions 1 and 2 to be satisfied. And a simple counterexample to convince you that this is indeed the case is assume that the control sequence is deterministic. In that case, assumption 1 is automatically satisfied. And so therefore, you can sort of think of xi as an inhomogeneous Markov chain now, where the transition probabilities are sort of indexed, if you like, by the actions in this deterministic sequence. And this inhomogeneous Markov chain may or may not satisfy assumption 2. If that inhomogeneous Markov chain is not weakly ergodic, then assumption 2 is violated. So you need both of these assumptions to hold in order for our sample complexity results to work. There's also a couple more sort of technical conditions. I won't emphasize this too much other than to point out that assumption 4 just says that the time to return to any state action pair is bounded by some integer capital T. And by the time to return, I mean the time between two return times to the specific state action pair. And this should be true for any ith time to return variable. So assumption 3 and 4 actually have a really important implication, which is that the time to return bound capital T should be at least as large as dk over 2, where d is the state space size and k is the action space size. So we will see that this pops up in our sample complexity result rather explicitly. I should also point out that this assumption 4, if we only restricted ourselves to a Markov chain, actually implies the usual minorization condition for a Markov chain. Anyway, okay, so under these conditions, right, so these assumptions 1, 2, 3, and 4, let's try to address question A. What is the sample complexity? So our first theorem establishes the sample complexity result. And essentially what it says is if I have a length m trace or sample path from my MDP, and assume that this MDP satisfies assumptions 1, 2, 3, and 4, then I make an epsilon error with probability delta, at most delta, provided the number of samples is greater than m0, which is an omega of d squared k squared term. So I need greater than d squared k squared number of samples in order for me to have an epsilon error with probability at most delta. Now there is an explicit form for m0, but I think what I would like you to focus on here is simply that if capital T is large, in other words, if D and K are large, if I have a large state space and action space, then this order t squared term is the one that's going to dominate, modulo certain logarithmic terms, which we can ignore for now. So let me sketch a proof of this result. So the proof is, I wouldn't say that it is, it is very technical, but it is sort of very natural when you try to prove it. So the first step is to just use a union bound. As I mentioned some time ago when I talked about that first proposition, you need to control the number of times that you visit the state action pair S and L. Right? So if you control that, then you can actually get a control on this error probability. So using the union bound, I can decompose this probability in terms of these two sums here. The first term is going to be bounded by the proposition 1 that I showed you. I think I can jump over there quickly. So this was proposition 1. So remember, if I have NL and NH, then this the probability that I make an epsilon error and the event that I visit SNL between NL and NH number of times is upper bounded by this exponential quantity. So let me go back here. The proof of proposition 1 is technical, but it uses a sampling theorem that was proved for Markov chains by Billingsley, and you can see it in his book on estimating Markov chains. And using this result, we can show that this first term is bounded by delta over 3, provided that m is larger than this term here. The key point is the following. M has to be at least an order t number of samples in order for this probability to be at most delta over 3. So that's an important thing to keep in mind. Now going to the second term in this inequality here. So now I'm going to focus on the second term. We will bound that term using an Azuma-Hefting type bound for general mixing sequences. This is a result proved by Arya Kontorovich and Kavita Ramanan in 2008. It's a very general result, and all that it assumes is that the sum of these weak mixing coefficients is finite for each m, and then you get this sort of exponential tail bound on the centered number of visits to the state action pair SL. Of course, the result in Kontorovich and Ramanan is a lot more complicated and a lot more general, so I've sort of specialized it to our specific setting here. Now, using this lemma and choosing NH and NL appropriately, we can then show that the probability of the second, the second term in that inequality is bounded above by these exponential terms. And this probability is going to be less than or equal to 2 delta over 3, provided that the number of samples is larger than essentially a t squared term. So if t is large, then that is the term that's going to dominate. So if you put both of these, the first term and the second term, and their bounds together, then the dominant term is precisely this t squared term. And therefore, you need a sample of size at least d squared k squared in order to guarantee that you have at most a delta probabilistic error. So some commentary about this result. The sample complexity result, as I noted, holds under significant generality. This is because of the generality of lemma 1 there, the Kontorovich and Ramanan result. We can't conclusively prove that the estimator in our case is actually minimax, in a sense that I will define in a moment under these assumptions 1 and 2, as a consequence of this generality that we've assumed. Note that the sample complexity M0, which is an omega of d squared k squared term, is actually suboptimal. It's suboptimal in the following sense. If I fix an action, then I should be able to learn the transition probabilities corresponding to that action with at least a d squared number of samples. And somehow in our analysis, using this sort of general setting, we end up with d squared into k squared rather than d squared into k number of samples. So there is something lost, right? So there is some slack in this analysis where we've lost some sharpness. And I believe that this sharpness is lost in this result because of using this Azuma-Hefting type lemma. And this is a well-known problem with Azuma-Hefting type bounds. And it's well known that other bounds, in particular the Chernoff-Bernstein type bounds, can provide tighter tail bounds. And you can see some commentary on this in Verschinen's book on high dimensional probability in chapter 2. But the price that you have to pay, so there's no free lunch in any of this. the price that you have to pay is that you have to impose stronger conditions on the mixing coefficients. But nonetheless, this tells us that there is a trade-off. Now, there is a subtle trade-off between the looseness of the conditions. Like, do I just assume summability of these mixing coefficients, which means that it's possible that the mixing coefficients are, polynomial decay, for instance. And, the looseness of the conditions and the tightness of the bounds that I obtain. So you have to, sort of play around with this a little bit. And luckily, there is actually a Chernoff-Bernstein type inequality for these types of mixing sequences. So this was proved by, so initially, we believed that we had to establish this result, and it took us a while to find this paper. This is by Merleved, Pellegrad, and Rio, around the same time as Arya Kontorovich and Kavita Ramanan's result, which basically says that suppose that you have these uniform mixing coefficients that are geometrically decaying with some geometric decay rate kappa. Then if I have a length m trace, then there is a constant, I'm calling it a Cp, which only depends on this geometric rate kappa, which only depends on this geometric rate kappa, such that I get an exponential bound on this error probability here. Okay, so I won't get into the details of this form, but I'll point out that we have to change our assumptions on the control or action traces and the state traces. In particular, we have to assume that these coefficients are now somehow exponentially decaying. And if we assume this, so we have new assumptions 1' and 2', and we use this new lemma 1', then we get a new version of the first theorem, which states that if I have at least m0', which is an omega of d squared k number of samples, then I get an error probability of at most delta with an epsilon error. Okay, but I have to assume also that this constant Cp is actually independent of d and k. I'll come back to that point in a moment. The proof, I'm not going to go into the proof again. We might run out of time. But essentially, it follows the structure of the previous proof. I have, using the union bound, I get two terms. The first term is again sort of bounded by using proposition 1. The second term, I will apply the new lemma 1' from Pellegrad et al. And make an appropriate choice of NL and NH in order to get the bounds that I require. So it's a bit subtle, but you can get this result. Now, there is an important fact here, which is I get this sample complexity bound that it's omega of d squared k, which remember is actually the right bound complexity, right? So the right sample complexity, in the sense that if I fix an action, I should be able to learn with d squared number of samples. So the total number of samples that I require should be, at least k times d squared, which is exactly what we find. But it crucially depends on the assumption that this constant Cp is independent of d and k, is independent of the size of the state space and the size of the action space. Now, Cp is actually determined by this geometric rate. In general, this geometric rate kappa is dependent on d and k. But for a large class of interesting models, for example, an MDP with a stationary Markov policy, this kappa will be independent of d and k, and therefore Cp will be independent of d and k. In fact, our results in the paper that we're still writing, we haven't posted it on arXiv yet. We hope to do it within the next 15 to 20 days. Our results actually work also for inhomogeneous Markov chains. And so that's another situation where the Cp will be independent of this kappa coefficient. And importantly, the sample complexity bound that we obtain is tighter than theorem 1. Now the bound is m0' is d squared, it's omega of d squared k, fits our intuition that it should be d squared k number of samples. And this automatically raises the question, is this estimator actually minimaxed? Or equivalently, is the sample complexity bound actually sharp? In the sense that if I have less than d squared k number of samples, am I not able to learn properly here? So in order to answer this question, I need to define a minimax risk in an appropriate sense. So the minimax risk that we are going to use here is, again, based on this probabilistic error. So I'm going to look at this probabilistic error over all possible MDPs in some class script m. And I'm going to look at the best estimator over all possible estimators of this transition kernel. And we can show, so our main result is showing that this estimator m hat L is actually minimax. So remember, m hat L is just this ratio estimator where I count the number of times that I'm in state S, I take action L, and then I transition to state T, and divided by the number of times that I see the state action pair SL. That should be L, not T. And so this estimator is in the class of all possible estimators, and it is the one that is minimax. For MDPs in the class M, which consists of MDPs that satisfy assumptions 1 prime, 2 prime, 3, and 4. Remember, 1 prime, 2 prime were the conditions that the control sequence is geometrically mixing, and the state sequence is geometrically mixing. That's 2 prime. So the main result, the minimax result, is the following. So for some specific choice of epsilon, zeta 1 and zeta 2 were those probabilistic bounds on visiting some specific set Si at time I. So I have some number between 2/3 and 1, and some number between 0 and 1/3, 1 over 33. The state space has to be at least 2 and divisible by 3. And you need to have at least one action. Then for any estimator, there exists an MDP in this class such that if the trace length is less than an order of d squared k number of samples. So if I had less than an order of d squared k number of samples, and I'm putting a tilde here to sort of mask some logarithmic terms, then I will have an epsilon error with probability larger than 1 over 2 into 1 plus pi squared. So there is some positive probability that I will make a larger than epsilon error in my estimation. So therefore, what this is implying is that if I have, at least d squared k number of samples, then I will clearly learn, and it is in fact sharp. So this is the first result that shows that the sample complexity of our of this sort of non-parametric estimator is sharp, and that the estimator m hat is in fact minimax optimal for the class of MDPs that satisfy assumptions 1 prime, 2 prime, 3, and 4. The upper bound on m, the way that we get the upper bound is by using the following intuition. So we construct an MDP, and I can show that. I thought I wouldn't have enough time, but I think I've gone a little fast. So I can show you the MDP that we construct. And the MDP that we construct sort of follows this intuition that if I have to estimate all of the transition matrices, that estimation problem should be at least as hard as estimating the transitions for a single state action pair. And this is not a sort of novel idea. It actually comes from a paper by Wolfers and Arye Kontorovich that was published in 2019 that actually established the minimaxity of this same sort of counting estimator for Markov chains, for ergodic Markov chains alone. But it was a little surprising to us that this result only sort of emerged in 2019 and nobody had established it before. Since I have a fair amount of time, let me show you the MDP counterexample that we constructed. So basically what we require is an MDP that has positive entries in the transition probability matrix. So let psi L here be some sequence of numbers that take values in -1 and +1 of length d over 2. So it's some like +1 -1 sequence. We'll assume that the control sequence is just an IID uniform sample from 1 through k. Okay, so I'm just going to take some action between 1 and k uniformly at random at every time step. And then the transition kernel is just going to be it's going to be constructed using these submatrices, these block matrices. So CL is going to be a d by 3 over d by 3 matrix with entries with the same entries throughout, 2L over d minus 2, which is why you need d to be at least 2. RL here is going to be a d by d by 3 by 2 d by 3 matrix. So this is going to consist of sequences that the sort of shifts of each other. They're like modular shifts of the same sequence of numbers. And then J and L are going to be fixed matrices with entries 1 over D in them. And so this MDP can actually be shown to satisfy assumptions 1 prime, 2 prime, 3, and 4. And we can and it's using this MDP that we actually construct the counterexample, and we show that the sample complexity result is sharp. I should tell you that finding this MDP is non-trivial. Like it took a lot of effort. We've gone through many possible examples to eventually find this one. So I think this is sort of the hardest part of this type of analysis, finding these counterexample MDPs. So finally, I mentioned 3 questions. The last question that I want to ask, and I sort of have only qualitative statements to provide here, is the question is, how does the logging policy influence the sample complexity bounds? So the logging policy is something that I don't know. If you look in the literature on offline RL, almost every paper assumes that the logging policy is somehow a stationary Markov policy. In a service system or a medical decision-making situation, I have no idea why a doctor would make a decision using a Markov policy, right? So it's not like I only look at, if I'm sort of deciding a course of treatment for a patient, I'm not only going to look at the state of the patient right now and then decide what to do. I'm going to look at the history of decisions that I made and take that into account in making my next decision. So there is some historical information that is important, but you don't want to go all the way back into history, right? You don't want to go all the way back to the beginning of the patient's life. So there is, you do want to forget, but you don't want to forget too quickly, is sort of the point. So the structure of the logging policy will influence the mixing properties of the control sequence, and that clearly influences the type of results that you can get. The So the mixing of the control sequence is influenced by the structure of the logging policy. So remember, the policy is a function that maps states to actions. But it's very hard to say, what type of policy structures will lead to, different types of mixing properties. But one example that I can quote to you is that if I have a stationary Markov policy, then it necessarily induces geometrically fast mixing for both the state and the actions. So that is one situation where we can sort of see this connection between the policy and the mixing quite explicitly. But generally speaking, this needs a bit of work that we don't know yet. How to connect the structure of the policy, the functional structure of the policies, to the mixing properties of the control sequences. But if we assume that the control sequence has geometric decay of the mixing coefficients, then we were able to show minimixity and sharpness of the sample complexity bounds. But if we assume that it is merely summable, so maybe the mixing coefficients are polynomially decaying, then we were not able to show that it's minimax. But this does not imply that the estimator is not minimax under assumptions 1 and 2, right? So it's just that we haven't found a MDP where we do actually need a d squared, k squared number of samples. We just couldn't find such a counterexample. We looked at it. Initially, we thought that we had it. Then we realized that our example was actually only giving us d squared k number of samples. So this is maybe an open question for these types of statistical inference questions. Okay, so I've gone pretty fast. I know it was about 45 minutes, so I'm at my conclusions. So maybe there's more time for questions. So the conclusions, the main takeaways that I want you to have from this talk is model-based and offline reinforcement learning are very natural in the setting of data-driven service engineering. If I have a service system and I want to engineer it in a data-driven way, I want to find optimal policies or close to optimal policies in a data-driven way, then this framework for thinking about these problems is very natural. And it is worthy of further study. In particular, from my perspective, statistical inference is crucial, both for safety considerations and for confidence in terms of deploying the policies that you've learned in this data-driven way. And we have looked at the first sample complexity results, but it's wide open. You can think about CLTs, you can think about large deviations. There's a whole bunch of questions to answer for these types of model-based offline RL methods. And finally, I think an important takeaway is when you're thinking about these problems, think of this subtle interplay between the mixing properties of these stochastic processes and the concentration inequalities that you want to use, and how these influence the statistical inference question. So you need to use your understanding of stochastic processes and stochastic modeling in order to, sort of answer these statistical inference questions meaningfully. And in particular, in our case, we have observed that these mixing properties certainly influence the tightness and the sharpness of the sample complexity bounds. So I'm about a minute and a half ahead, so I will end here. So thank you for your attention, and I'm happy to take any questions that people may have.